question. Okay, good. Got it. Alright, so first off, this is my first presentation, so I probably can't tell already. So let's see. Give you a little bit of my background. I've been writing code probably for about 6 years professionally. Mostly doing automotive administration stuff, which is kind of good when you kind of transfer over to the pen testing kind of realm. Most of the target operating systems that we targeted were mixed, so we were doing stuff for Windows and Linux, which kind of led naturally to start using something that was cross-platform, like Java. And now in my current job, I don't actually write a lot of code professionally, but we do still use a lot of it to automate a lot of our pen tests. So yeah, so let's go forward and all right, so why Java? All right. So what people really seem to like are hate Java, they're pen testers. I think it's for noobs, and so you tend to catch a lot of shit when you talk about how you want to write in Java. They think it's not cool. They usually like Python, C, all those kinds of things. A few good reasons is it's cross-platform form, so it'll run across everything. You can run on Windows, you can run on Linux, Unix, all kinds of good stuff. It's got lots of libraries. I'm really lazy, so I hate writing new code. And so they give you just about anything you'd ever need. So that's always really useful. And I guess when you need to find something, you can usually go online, Google it. 50 million people have already done it before. So you just copy, paste, and you're good to go. Another reason why I really like to use it is because it's widely deployed. And Oracle likes to say that they've got it on like 3 billion devices. Every time you install it, they like to brag about that, say how many things it's on, which is really good for us pen testers when you're trying to find people to run your stuff on. You can kind of assume that it's probably on that box. Alright, so let's talk about what I came here to talk about. We have a problem here when I'm writing security tools, and I'm using Java. So one of the things I'm pretty used to in most of your native tools, like C, is if I want to execute shellcode, it's pretty trivial. You can actually just kind of put your shellcode into a buffer. You can kind of just put a function pointer at it, and you can call it right away. But how do we do this in Java? Since Java's interpreted code, you really don't have access to that native code. And so it can become quite a problem trying to get to those functions to be able to do this. Like I said, in C it's pretty trivial. This is our example. You're just going to stick your shellcode in there, point right at it, and you just call it. Real easy. Java does give you some possibilities for doing this. They have a JNI, and they also have JNA, which requires you to actually write C code that exports certain functions that then you can call directly into from Java. Problem with that is you're writing extra code. So you have your C code, you have your Java code. One calls into the other. You always have to bring that code with you. So if you deliver it, you don't know it's always going to be there unless you put it on that system. It should be kind of clunky. A lot of times, if you were to deploy that in like enterprise level, it could probably get a virus signature or something like that if you're doing the kind of work we are. Let's see. So to try to solve that problem, I went to the internet and I tried to find the different ways that people were doing things. The first one I found was this guy, and he was using the JNI technique I just described, where you go out and you write that deal out, and you hope that you can push it along and nothing bad goes wrong. And the second one, after lots of searching, was this little-known project called Java Payload that I found first in source storage and eventually moved it over to GitHub. There's a lot of code in there that I actually don't know what it does. It seems really cool, but I haven't had time to look at it. But I did find one class that was really interesting. It was called the JIT Shellcode Runner. And at the very top of it, I found this. And so I got really interested. I wanted to figure out what I was doing. So, first thing I did was I downloaded the source code, executed calculator, and saw what happened. And nothing happened. So I was like, all right, why does this not think this thing doesn't work? You know, I got really confused. I was like, this guy says this code works. So I started reading these comments. I saw the last thing I worked on was 701, which was released actually in October of 2011. So I was like, well, maybe this has something to do with it. I probably need to look into this further. So I started exploring a little bit. And got that particular JVM that he said, and this thing popped up, which is always really good. So if you're like writing any kind of exploits, usually I try to test things with the calculator, just because it's real simple to make sure everything works. So put that calculator shellcode in there, let it fly, and if you get this, you're really happy. But anyway, so now that I knew that it worked, I wanted to really kind of figure out what was going on. So I started actually looking into the code, trying to figure out why it worked on this particular JVM, but the new ones, it didn't. So started reading through the comments again. There was very little. The guy didn't really give much comments. But I emailed him. And by the way, if I hadn't mentioned, this guy's name is Michael Sherrill. I don't know if I left that out. Probably I should tell him. But yeah, he was a really nice guy. I actually emailed him to figure out how he was doing these things. He emailed me back, told me lots of good information to kind of go further with everything. So I figured I'd go into a little detail, give you all some explanation. So we'll see how this thing goes. All right. So once again, just get a little refresher on Java. It's an interpreted language. It kind of takes what you write, turns it into bytecode, and then that bytecode is interpreted by the JVM into native instructions. Now, one thing they added, probably, it hadn't been too long ago, maybe 10 years, so not a little while. They added the JIT compiler, which takes Java instructions that you actually run a whole lot, and it will on-the-fly compile those into native code and cache them. So if you run them a lot, you'll get your speed performance almost as if you're writing native code. So one good thing about this is this means that our Java JVM has native pointers somewhere, and it has native code that we might be able to get to. So now that we know we can get to this native code, we got to find out how, so that we can put our native code in it, replace it, call it. So the good thing is Java actually provides us a way. I mean, it seems to provide just about everything. Might not be that documented, like this particular class called the unsafe class. So the unsafe class, it's a Java Sun proprietary class. They use it for doing concurrency classes. They don't really want you to use it. It allows you to directly access memory. The reason they don't like it is if you are to use this incorrectly, it will crash the entire JVM. So whatever application you have is just done for, and you can't catch it because it's a native exception, and they don't like catching those. Let's see. So to try to figure out what we want to do to get from the point I had showed earlier to try to find that pointer to that native code from where we're at, we actually have to walk the memory structure of the underlying Java classes that are native and try to find those pointers so that we can then replace it with our own code. So the general algorithm that Mr. Sherrill came up with was first he obtained the address of a static member inside a class. So once you find a static member, then you find the pointer to another structure that actually keeps track of all of the methods in that class. And so what we're looking at here is actually the internals of a class in Java. So if you were to actually break it down and look at what it looks like in like your C++ native code, this is actually the internal structure of that class. So you can see some of these, as you can tell, are integers. Most of these are addresses. And what he figured out was that there's always a pattern. So he pretty much developed indicators so that he could figure out where the particular pointer he was looking for was. You'll see these 3 arrows point to what he decided were pretty much consistent across the JVMs, so that he could find that one right there. It's called the method array pointer. Once he found that method array pointer, he would step into that. And each one of these pointers actually is a method structure. And inside this method structure, there will also be another structure to the actual native structure. So we're getting closer. But so that native structure will actually have our pointer to where we want to go. So in this one again, we have 2 more indicators that he also found will generally be like 3 steps above the native method structure, and they will always have a certain pattern, or it's close. And then once we step into that native method structure, then we finally have our native method structure, and inside that is finally the pointer that we're looking for. So once we found that pointer, we get to the fun part. So once again, that unsafe class, it has methods in it that you can actually write to memory too. So once we get this pointer, we actually just call into it, start overwriting all the bytes that are in that pointer that was compiled by the JIT compiler with our shellcode. And then once we do that, we're going to call it. So the issues that I started figuring out between what he had originally written and the JVM that I downloaded and didn't work was, it turns out these indicators that he was finding aren't exactly consistent across all these JVMs, which makes a lot of sense because this code is ever changing and they're probably adding new methods, new fields to these classes. So the good thing was the actual sequences that he found were consistent, just the place in the class changed. So they might move up a few, they might move down a few, so the offsets were actually different. So what I ended up trying to do was get in there and actually try to automate the process of finding those. So pretty much kind of brute force things, walking those trees until we found those indicators so that we know where we were. Another one of the problems was between our 32-bit and 64 JVMs, Java decided that the pointers that they used for their address spaces were too big in 64, so they came up with a way of compressing your pointers, which became kind of a problem for us because we have to determine which ones are compressed and which ones are not, and then run it through yet another algorithm they provide to decompress it and try to go forward with brute forcing these indicators again. Other than that, the biggest problem I found when I was trying to, like I said, make this work across everything was starting with Java 1.7, they actually added a realignment issue at the very beginning. So as you can imagine, once you start in on the process of trying to dig down on these different pointers and such, and these structures, it's okay if you already know where you're starting from. But what they introduced was they moved the very first pointer. So the problem, once again, is using these unsafe classes. If you pick the wrong pointer, the whole JVM crashes. So you're done. So I had to figure out a way that if the JVM crashed, we could proceed. And that's where I ended up writing yet another brute forcer at the beginning to try every one of these offsets, and if it crashed, just parse through the output data, say this is pretty much a failure, and then go forward until we actually found the right one. This is kind of, explained all of that. But yeah, this is what the picture of kind of what I was talking about. So we have our original JVM. We passed an offset of what we thought might be that very first pointer. We try it out. If it crashed, we go forward. If we got the success, we go on. And that way, this one was safe, and we could proceed afterwards, and this one wouldn't matter. So now for a demo. So I figured the first thing I'm going to show, just a little bit of the class structure and how this stuff works, just with the code that he had originally that I modified. And then if I have time, which I'll probably do, because I'm talking really fast, is show one of a practical application that you might be able to use in a pen testing environment. Alright. So in this example, right here, I have some shellcode that actually executes a calculator. I generated this through Metasploit. And one of the issues that I'll get into later is when you're following this stuff from Java, you have to fix up the stack correctly or it will crash. And that's what this extra code is. You'll see we have some extra things right here. But set this breakpoint here so you can see, as I was mentioning, we did all the code to go figure out where everything was. This right here is actually our native pointer that I was talking about, which is the one we want to replace. And then this code goes ahead and puts in all of our shell code. And then immediately after it, we run it right here. So, run it. Yeah! Over there, alright. Love success. Okay. So that's kind of like our little proof of concept. All right. Just a few technical notes before I went on. Inside the actual method that we're going to be replacing with our own code, if y'all do ever decide to go look at this code so that you can, expand upon it, use it for better things, you see a lot of this really random stuff. I got really confused when I first saw this, and so I really needed a good explanation from Mr. Sherrill, because it looks like just randomness. But he then informed me that these volatile instructions right here, this particular member that we're incrementing and decrementing, their volatile ints, actually cause the JVM to create a whole lot of memory, and it will make a bunch of native instructions to do these very simple things. And he actually put them in this order so that when it's being interpreted, it doesn't get optimized and rip out a bunch of this code, because every time it writes these, it will make that buffer that we want to put stuff into larger. So, like I said, it looks really crazy, and there's a whole bunch of these blocks. So, as he described to me, if you want to make room for bigger shellcode or whatever, you can just copy more of these blocks. And if you do decide to actually debug through, you can see how big of a buffer it's making for these, if you want to verify. That's actually another tidbit that I need to probably throw in there. A really cool thing about this technique, that breakpoint I just showed y'all, if you do know how to use like immunity debugger or WinDebug or anything like that, you can take that actual address, you can plug it into your WinDebug, set a breakpoint, and you can actually watch the shellcode running through a native debugger and verify a lot of these things. You can verify what shellcode you're running, how big these buffers are, and a lot of that kind of thing, which is actually kind of become a dual purpose for me when I'm developing exploits. And I just use this as a super quick. I can just plug it in there and start debugging straight through my shellcode. As I said earlier, another caveat that you really have to worry about when you're trying to run shellcode through this particular technique, when you call in from Java into your shellcode, it has the stack set up in certain ways so that when it's done, it will come back into the JVM correctly. So you have to keep note of that and realign your stack when it comes back, or once again your JVM will crash. And that really, you can't really get around that. Which why actually for the second demo I was going to use the Metasploit one, but the MSF payload utility that it has produces shellcode that really mangles up the stack. So as of right now, I don't really know how to recover it. So let's go to our second demo, and I'm going to try to do another calculator, but we're going to use Metasploit this time.
So this is your first talk, you thought it would be a good idea to have two demos. Yes, just go for it.
I figured I
go.
All the time. I saw it in my talking points. Yeah. All right.
I'll let you know when you have 5 minutes. 5 minutes.
So here. That's way too small. Alright, so in this box, we have a Metasploit listener, and we're going to be listening for a Java payload. So we actually use a lot of Java payloads in the kind of work we do because, like I said, it'll work across anything. So it's really nice to be able to send out one thing and know with pretty good certainty that you'll get a lot of callbacks because it'll work on all the operating systems. So we're going to assume that we're using a Java payload, and we'll set up this listener here and call that to it. So in this Windows box, so we got more calculators running. On the desktop, I have a Metasploit jar. There, people.jar. Normally, you'd probably deliver this in, an evil applet or maybe through a phishing campaign, put it in the macro, something like that. If we run this.
Nice on Minecraft,
We go back and see we got us a nice interpreter shell. Find my mouse. There you go. Alright. Make sure we're on the right place. Okay.
Yay!
Alright, so that's just that. So I put together just a proof of concept for this. Wrote a little extension. We called it Shellcode runner. And we have this little function here where we can provide whatever shellcode we want, and we can see if it works. And this is that same shellcode that we just looked at. Yeah, right now it's pretty hacked together. If I make it cleaner, take some time. Go back over here. hopefully. Here's your calculator.
Oh,
Right. So that's our little, what you could do. I mean, you could always fill that with, like I said, an interpreter shell or a rat, and then you sort. You just have to make sure, like I said, you set everything up right so that it doesn't crash your other shell if you want to keep it. All right, so all right, that's it. You don't have any questions at all?
Have you tested any of the techniques against OpenJDK?
I haven't. Yeah, most of the stuff I use is Oracle stuff, just because it's easier to download. Yeah, I really don't know. I would hope that it would work, but I can't say for sure. I haven't checked it. But yeah, right now it works against 32 bits, 64, 1.6, all the way up to 43, and 1.7 up to about 45. I guess we're at now.
Question: are there any changes to the Java policy that need to occur in order for you to execute unsafe code?
No,
Or
see,
use
that's
that
that's
Java
part.
file?
This actually isn't an exploit, which is a kind of fun thing, because when I first wanted to talk about this, we had to get a lot of approval because it scared a lot of people. They thought this was an O-day. But this is how Java works. It'll be here probably as far as I can tell from now on, because it has to talk to native land. So these pointers are going to have to be there unless they get rid of that JIT compiler. So it's really no way around it.
So there's no security policy that needs to be relaxed in order to use that functionality?
No, this will work out of the box on any JVM.
Security policies that you can enable to prevent this exploit.
As far as I know, no. Like I said, because it's not an exploit.
It's just native built into Java and
Right.
live with the vulnerabilities.
Yeah. I mean, and that's the thing. Like, so if you think about it in terms of like, the programming language, like I was mentioning before, like this is possible in any native language. So it's more of a feature than a vulnerability.
Are you aware of any research where people tried to get this code injected into an application that didn't use unsafe?
I think, and like I said, I'm not positive because I didn't look through much more of Mr. Sherrill's code, but I think that's actually what most of his project was about. Was he was just using Java to do pen tests similar to Metasploit, and so I think he'd figure out ways of actually using things like this and other techniques to hack running Java applications using this, using things like their remote Java debugging and that kind of thing. So there's probably some stuff there. This particular class isn't related to that. This is just a way of running shellcode, but it's possible.
Yeah, and I guess to further his question, like, why does Java let you override random pointers? I thought the whole point of Java was you couldn't do pointers.
Yeah.
It was safe language.
I mean, I'm guessing they could probably restrict that unsafe package, but since it's also just Java code and it's been out there for forever, I mean, it's already out there. Probably people would just pass around that class, and they have to do something serious, I guess. Anyone else have any more questions? Like I said, I'm Wincey. Here's my contact information. Thanks for letting me talk. I want to thank the boss for going through the hassle of getting this approved for me. Thank Mr. Sherrill for all the hard work. I know he's really busy, or he's probably doing lots more cool stuff. This kind of blew my mind how he figured this out. But yeah, I'm going to try to put it up on GitHub soon. He has his own, but mine's changed kind of significantly from what he was trying to do, so I don't know if it's going to be able to be merged directly into his stuff. So I might just put it up separately. Same with the little Metasploit POC. So check it out.